answer
Okay.
section.
Thank you for joining us. Also, I would like to welcome Jos Melkonian, one of Dr. Walter colleague. Uh, and we already have 30 participants in the meeting. Without further delay, I would like to uh, invite you to present your content, and the floor is open. You can present your content, Dr. Walter.
Okay, I will share my screen here and start my presentation. Oh, sorry, this is not this is not the right one. You can see my screen?
No.
No? I will try again. Sorry. What about now?
Yes, it is visible now.
Okay. So, I'm going to talk about our experience, maybe from Uruguay, mainly from Uruguay, along for more than 20 years, modeling the geoid. My talk will be about the first presentation from my country, my institute, some geodetic network that we have at the Geographic Institute, some geoid application that most of you must know, and then the methodology for geoid modeling from 2000. That was our first model, Geoid 2000, and then an improvement was did in 2007, and then in 2022 we made a preliminary geoid, and then our final geoid that was released last November. I will try to talk about our experience and what challenge we faced, and our future in geoid model. About my country, I will make a very short presentation, but my country is here between two very big countries, that is Brazil on the northeast and Argentina on the west. We are a very small country with 1,076,000 square kilometers and 3,004,000 more or less people. And our terrain is very, very flat. Our mean altitude is about 75 meters, and our highest mountain is 500 meters, 513 meters exactly. So we have many advantage modeling the geoid with that a small and flat country. And this is for you understand also what the advantage and disadvantage we have. My institute, the Military Geographical Institute, was established in 1913 to produce the official cartography for Uruguay, military cartography in the beginning, and is responsible now for all the geodetic, topographic, and some geophysic networks as gravity and magnetizing. He also maintains an active and passive GNSS network, and also integrates several institutions, international institutes, and currently has the president of the SIRGAS project. So here are very old pictures. This is a base camp for measure a baseline here. This is in 1930 or more or less. In that beginning, there was not any equipment to measure distance, so we had to make on the field, and we have several bases from 9 kilometers to 11 kilometers in Uruguay. This is one guy making measurements, and this is another step on the Geographical Institute. This is the Earth photogrammetry in the 1950 and 60. This is also a wheel B8 equipment. And this is our highest peak, highest mountain in Uruguay. It's called the Cordillera, and it has 513 meters with 67 centimeters. 513 meters and 67 centimeters. So it's, as you can see, is very flat. In order to understand also our facilities to model geoid, I will present two networks. This is the first one, the vertical network. As you can see, we have 8 polygons in first order leveling network. The second order, we have 42 polygons, and the third order, 140. Right now, at this moment, the first order and almost the second order is totally recalculated in geopotential numbers, and we have also normal altitudes and orthometric altitudes from that. And we are finishing the second order, and this year we are going to start with the third order to complete the vertical network. So this was a big effort because mainly the first order here, the red ones, we have to go to the very old field records, something that measured on the 1930s, 40s, and 50s. So it was very difficult to find the records and then to translate into some digital form, but we made it finally. And this is our gravity network. As you can see, we have almost 2,400 relative points, that is the green ones. And we have at this moment, all those red ones are absolute stations. Two, one in Brazil, that is a small one here, and the other one in Argentina here. This is Argentina and this is Brazil, and the rest one are in our country. Especially this one here, I would like to say that this will be our next vertical datum. We have now, at this moment, a vertical datum established here in Montevideo, at the capital. And we are going to calculate a new vertical datum here in the center of the country with a geopotential number in the frame of the International High Reference System and International High Reference Frame. The station is already made, and we are ready to calculate this year, maybe in the next month, a new vertical datum for Uruguay, and then to recalculate all our vertical network and also our gravity altitude. So this is in the frame of this project I mentioned, and also we have to decide which kind of altitude we are going to use in the future for Uruguay, if normal or orthometric. We are going to see in some slides that is not too much different between the two. And Geoid application really don't, most of you know which application Geoid can be used for. For example, here for us it's important for the implementation and monitoring sea level with some centimeter or maybe better precision. And also you can use a Geoid for the digital terrain model generation, and for topography, geodesy, cartography control, and also for geophysics, and mainly for investigation of natural resource. This is very well known. And here are some general concept about we use for modeling the geoid in Uruguay. First of all the programs are from the Geographic package. It's a very nice package made for along the years for Postweb, who is here, thank you again, and Cherning, and they spent many years improving and making new program and including this in this Graphisoft package. It's very nice and very easy to use and very friendly. So, and you must know also because the Nepal Geoid in 2011 was made with Graphisoft. The technique is the remove restore. Now they are calling remove calculate restore, but it's the same technique with the Stokes formula and some modifying kernel in order to avoid the lack of gravity all around the world. This is a very common graphic that displays the contribution or the three main parts of the modeling the geoid. The geopotential geoid here, that is the straight line, and if we have some gravity data, we can get a more tailored geoid here, and if you have terrain data, finally we have a very precise or more or less precise geoid. So we use the best geopotential model available at the time of the calculation. We tested first several 1, 2, 3 models for Uruguay, and then use at the highest degree and order possible according to the test. And also we try to use some geopotential model that has some combination of more than one kind of satellite, and also, if possible, terrestrial data. Here is a key point. We always ask for new border gravity stations in Brazil and also Argentina. We have a very nice collaboration with the official institute in both countries, and we exchange our data in order for them model the geoid in Brazil and Argentina, and also for we can model better our geoid model here. Always improve our database and we merge it with the bathymetry and sea anomalies model at the German Technical Institute. Always they make a very big and nice work making this model that is very useful for us. Also for terrain, we are trying to find the best data available, and sometimes the final decision about the model and the resolution depend on the computer facilities. Also, we use for terrain the residual terrain model reduction for gravity from Fosler again. And also, always we have some stations, GNSS, and vertical orthometric station, and we use to separate this station for validation of the models. That is more or less the general view of we use to do along the years. So let's talk about the first one. Our first geometric model was in 2000, and it was a gravimetric geoidal model and a transformation model for the vertical datum in Uruguay. That is because after we calculate the gravimetric geoidal model, we have to adapt for the vertical datum. In certain way, we are destroying our geoidal model in order to adapt this for the vertical datum. We use the remote restore techniques using the rigorous stochastic kernel via one-dimensional fast Fourier transform, and the free air anomalies was reduced at the geoid. With the normal procedure with free air anomalies and Bouguer, and also some terrain corrections. So that is, we obtain straight to the gravimetric geoidal model. Our geopotential model, in order to have some global data, was the EGM 96, degree and order of 360. That is about a resolution of 55 kilometers on the Earth. We had some more than 15,000 stations inland, more than some model for the free air anomaly at sea, that it was that model at that time. On terrain, we have more than 260,000 points, sorry. And in Brazil, we have some DTM from Brazil and Getopo 30 of Argentina. And we have also some control station, 22 for the transformation model, 23 for validation, and some Argentinian station, but very few, 29 also. So this first figure here shows the distribution of our gravity station. As you can see, we have in our country here several holes still, and here we have a very big lake, so we have no information. And also in Argentina, it's only main circuit of gravity, so the border are not so good. And this is the final geoidal model. As you can see here, is between 70 meters, positive 70, through 11, 12 here. So around 5 meters of the difference between the lowest point here in the east and the highest point here, more or less. And the absolute precision of that model was the 25 centimeters and 0.2 ppm for some stations. This is what was our first try on geoidal model. In 2007, we decided that we have enough new, mainly geopotential models that they develop very, very fast. We have also some new gravity stations. And after the Geoid school in 2006, we first made in Uruguay a workshop on technique for modeling the geoid. We followed the Geoid school and the New Mexico's exercise from René Fosberg. So we have a workshop on 5 days. And the final exercise was the calculation of the Urugeoid 2010. So this is different because this Geoid 2007 was first calculated as a quasi-geoidal and then a geoidal and then a transformation model. So we have 3 different models here. First, the quasi-geoidal model using the high anomalies. Then we transform via Vogel anomalies these quasi-geoidal in geoidal models. And then we adapt this geoidal model for the vertical datum cabinet. It was used also the remove restore techniques also with some modification of the stock, the kernel of the stock, via also the one-dimension fast Fourier transform. We always use the Fourier transform, but it's very fast and accurate. And in this geoid, we use a modification of the top that using one dimension with only one parallel. The one dimension fast Fourier transform gave the same result on the parallel at the integration, at the rigorous integration. So we use that. The geopotential model was the GGM02Z, degree and order of 360. And we have some more than 70,000 stations. Land and the model for C was the KMS02 model from the DTU from Denmark. The terrain, we have something like 3 million points from SRTM and some model for bathymetry also was the DNS05, 2 minutes. And the control station, we have 50 stations to control the geoid. And this was the final geoid. And you can see our absolute precision was the 10 centimeters more or less after we validate with some stations. That was our Urugeoid 2000. And then in 2022, we again decide, we decide again to improve our geoid because we have many new gravity stations, mainly in Brazil and Argentina, some in Uruguay, and we have also some absolute stations. And we made also readjustment of our gravity network based in some absolute station. That is a project that started on 1995 with the Hanover University, and is still working. So we readjust the last year our gravity network, and then we are in this moment we are readjusting our network again using the whole set of absolute stations that you see in that previous slide. So our preliminary geoid was again our gravimetric models, a spherical stock formula using high anomalies, and we separate the geoid having components of different wavelengths, of course, as we can mention. And the land we use the residual terrain model plus the second method of Helmer condensation for the direct effect on anomalies and the indirect effect on high anomalies. And the transformation and evaluation, we have some 3 set of GNS and plus 1 standard one. So the data available and use it. The model, the geopotential model was this one, Eigen 6C4, and this one, to the degree and order of 2190. Gravity, we have new campaigns in Uruguay, in Brazil, and Argentina, something like 2,000 stations, gravity stations. And we use the DTU13 free anomalies, and for terrain SRTM30 and DTU18 for bathymetry. And then we may grid from 15 seconds, 30, 60, and 120 seconds of terrain. In control, we have this station 51 to make the transformation, 45 for validation, and then we have another set of 51 stations in Montevideo, a very small area, plus some data in Argentina and Brazil. So we first test the geoidal model over 22 GNSS stations, and this is the Eigen model, and this is the SGG model at the degree of 360, 720, and 2190. So this is the result. They are very similar, and in the degree very small difference. But we note that from degree 30, 360 to 720, there was a very big difference in the standard deviation, and also the range dropped almost half. So between these two, we decided to use the Eigen 720 at the degree of 720, because this Eigen model has GOES, GRACE, and Lajeos satellite, and also several ground stations. So we decided to use this one because of that. But the difference really is almost nothing. I think both of you can be used without not much difference. This model is from 2020, and this is from 2014. So this is our preliminary data in gravity. You can see here a very big number of stations in Argentina, and here also very big number of stations here in Brazil in the border, and also here in the left, in the right corner here. And also this is for terrain. You see that maybe this one is 400 meters here, 300 meters, and here our highest point is around here, 500 meters. And we have also the Atlantic Ocean here with a very big trench here, about 3,000 meters deep. So as you can see, we expect some improvement here in the border, mainly here with this data. So this is the control station in red, and for transformation, for validation are the green crosses. That we try to find the best possible distribution, but also we have some holes here. Still, we have to improve that. When we compare some statistics, this model with the forecast station, was 0, with the standard deviation of 70, and the minimum and maximum was about here. It's between more or less 20 centimeters. And this is the first the station in a very small area near Montevideo. It was very consistent here, 3 centimeters. This was to test in the small area how is the behavior of the geoidal model. In Argentina, we have a 245 station, and the mean was that one, 67 centimeters. And for Brazilian station was 38 centimeters. We had to make some transformation because the Argentinian vertical datum is different from Uruguay, and also the Brazilian one. So this transformation is not very accurate, but we use the values that we know through the SIRGAS project in order to normalize all the stations at the same vertical datum. And we know that the difference between Argentina and Brazil is about 30 centimeters. That is well reflected here. So I think we are more or less in the right place. And finally, our Urugeoid 110 because our institute this year is having 110 years from its establishment. So that is the first time that we changed the name of the model, and the version is 2023. The methodology and technique is the same, but terrain is not, and I will explain later. The data available, we use again the eigen, and the gravity station are the same 20,000 station, but in terrain, we have some, for Uruguay, some survey from LiDAR at the 2.5 meters resolution. So we use this for Uruguay. And in Argentina and Brazil, we use the SRTM30. And from bathymetry, we use the DTU18. So finally, made some grids with the highest resolution was 6 seconds, is something like 180 meters on the surface. And from control, we have the same station as the previous model. This is the difference in terrain. Because of we have more than 104 million data points, terrain data points. We have to change our strategy for managing the terrain data. So we divide our, this is 8 degrees by 7, more or less, and we divide this area in 4 big squares here for land, and also for gravity is this one here, with some overlapping area here also for land. For example, this B1, block 1 here is going up to here, and also the B2 is going up to here. So we have here some 80 kilometers of overlapping. And for gravity also we divide in 4 areas. This is gravity G1, G2, G3, and G4, with also some overlapping area here. So in the remove restore process, each block was strictly separate. And for example, here the air anomalies was subtracted from the EGM model for each model here, for each block here. And we produce here a block 1 air model, air free anomaly, B2, B3, and B4. And also for gravity, we also use to reduce gravity from the geopotential model and produce another set of files here. And then we calculate all the effect of terrain here and integrate in only one. In this step here, we reduce the free air anomalies from the GM, from the previous step, and then we reduce from the terrain contribution. And then the final effect on from terrain for high anomalies was integrated in also in only one file. And this is the same here for terrain. This is for gravity, and this is for terrain here. So we calculate the effect on terrain and high anomalies and produce another file here. So on summary, we treat gravity here, make the remove process, and we also calculate the indirect effect on high anomalies here, and also calculate the effect. From this step on, we join all the files and treat the model as only one. I would like to show here the quasi-geoid and geoid difference is between the high anomaly, the normal altitude and orthometric altitude. So this is the difference between the two surfaces. The quasi-geoid is related to normal altitude and the geoid to orthometric altitude. So as you can see here, and this is the 0 millimeters, and most of the countries between 0 and +1, -1 millimeter. So really there is not so much difference. And this accurate for our geoid model, there is not so much difference. And this is our geoidal model. As you can see, again, from 11 meters here up to 17 meters here. And here we have some big anomaly. That is because the layer here push to this side here. And this is the statistic. The mean was over 45 station, and the mean is 1 centimeter. The standard deviation 8, and it's more or less 20 centimeter range. And for the Argentinian statistics are better here. If you remember the last slide, the mean are very nice here. And also the standard deviation is the same for both. And also the range is between 20 centimeters and 20 centimeters. So the problem with the compare Brazilian and Argentina station is that distribution of the station is here. It's very, very weird, really. We have just here station and just here, and some isolated station here. So it's not, the distribution is not so good, but as the station here and the station here are in the new gravity surveys, that is because our statistics are okay. So some slide here to show for the future. What we are going to do to improve our geoid. First, our simultaneous adjustment of the vertical network in geopotential numbers, and as I mentioned, a new updated vertical datum in the center of the country, as I showed. The readjustment of the gravity network, including new station of absolute gravimetry and relative measure in recent years. That is a project, as I mentioned, together with the Hanover University, and we are making this readjustment at this moment. We are making some field survey in order to connect the absolute station to the gravity network, and maybe next week we will have a final result for our readjustment. As I mentioned, the previous readjustment of our gravity network gave a mean standard deviation of 26 micrograms for each station, with a maximum of something like 50 micrograms. So we have in Uruguay, we have a very nice gravity network. But we need, as a point here, better distribution of GNSS stations, maximum of 50 kilometer distance between the stations, in order to transform the geoidal model with more precise results. And also, we have to investigate all the variants of the geoid calculation methodology, including the mass density effect, how to integrate the geopotential model, and there's now a new geopotential model to analyze with the better satellite information. So this will be a challenge for us. And some experience and challenge. But the best part is having a free geodetic software package, as I mentioned, Graston, well tested, and a technique for geoid modeling, very nice and very known and easy to follow. The data collection is the most difficult part and time consuming. Really, it's very hard. More than 80% of the time of calculating geoidal model is to gather the data and also to assess the precision of the data. For that, regional and international institutes collaboration are very, very important. And what about the geoid spectrum? I show that figure when we divide the frequencies in several parts, but how to match this global geopotential model at what degree and order, in order to not to produce any hole between global data and regional data and also local data. What is the best match? How to do it? That is maybe wrong and right trying to do, and experiments very several ways to do it in order to see how this is the behavior of the geoid. Also for the terrain, what is appropriately treatment and what is the quality of the data. That is another challenge. And finally, what kind of best geoid is according to your available data? Is the gravity data, or is just adapt some global geoidal model to your vertical data? I don't know. It depends on the data that you can have. And thank you for your attention. Let's go to the question and answers. And sorry if I've made some mistake during my presentation. And thank you very much.
Thank you so much for your presentation, Dr. Walter. Now, I would request all of you to ask if you have any queries regarding the presentation. You can also put your question in the chat box, as well as you can also turn on your mic to ask question directly. So now we are entering the Q&A session. Again, thank you for your presentation, Dr. Walter.
Okay. I would like to say something before the question and answers. I don't know really in details about your geodetic networks, the Nepal geodetic networks. I was reading some papers before my presentation, and I also went to Google Earth in order to know better the geography of your country. You have a very big challenge because the northern part of your country is very high, and you have also some plain part, some low part on the Indian border. So I think one of the challenges is how to define the use of the terrain data that you can have. Also for gravimetric data, as far as I know, maybe I'm wrong, you have one absolute station, and I can recommend at least 2 or 3 more absolute gravity station in order to make a readjustment, also improve the gravity network. It will be nice, but it of course depends on the international collaboration. And I don't know exactly the distribution of the gravity data, but I think because of the geography, of course, it's not the best for a geoidal model. That is my first comment. So,
okay,
I'm ready. Shoot it.
Okay. If anyone have question regarding presentation, please you can ask directly the question.
I'm a little curious, Dr. Walter. What is the elevation range in Uruguay? You just explained the geoid model here. What is the elevation range? Because in Nepal we have elevation range from around 60 meters to 8,800. So I was curious, what is the elevation range in Uruguay?
Okay, Sushmita, thanks for your question. As I stated at the beginning, our country is very flat. Our mean altitude is 75 meters, and we have some part of the country with 300 meters and 400 meters. and our highest, our Everest is 513 meters with 67 centimeters. That is because we're very flat. That when I show the difference between the quasi-geoidal model and the geoidal model, the difference is some millimeters. So
Yes.
it's really not much difference between normal and orthometric altitude.
So what can we expect in case of Nepal? Yeah, what can we expect according to your expertise? If we derive the difference between quasi-geoid and geoid model for Nepal in such variation of height, elevation, can we receive such type of accurate data that you have shown before, the statistics you have shown? Very nice statistics indeed. Is it possible for a country like Nepal, which have variation, so much variation in elevation? Or you have any suggestion you can provide?
Okay. I was thinking exactly this morning, exactly that question. What can you do? I think I present the division of my project in 4 blocks from different blocks. And I think maybe you can use the same idea and divide your area in a highest mountain, maybe in 2 parts, and a lower part of the Nepal, maybe in 2 one. So maybe divide the country in 4 with some overlapping areas, but it depends on the data that you have. As I mentioned, we was very lucky because we have a LiDAR survey 4 years ago, and we have a resolution of 2.5 meters for terrain data. But in your case, I don't know what DTM model you can have. But I think you have to divide the area in order to assess first the accuracy of the terrain data, and then to treat separate each part. I don't know, maybe I was thinking this morning this kind of problem that you face. I don't know if you have a DTM model or not, or you depend on the global DTM data. There's Copernicus, for example. There's a new one from NASA called Aster that is supposed to be high accuracy, but in Nepal, I think the best accuracy is for the plain part of the country, not for the high mountains. I don't know.
Yes, it's true. Thank you, Dr. Walter.
Okay, thank you. Anyone having question further? You can turn on your mic.
So another comment. As I mentioned, you have a very nice software package. It's GraphSoft, and it's very easy to manage, very easy to use it, and we have a very well-known procedure for calculation geoidal model. I think you can start trying to do something. As I mentioned, I think I forgot to mention, but we are going to make this year, maybe in October, November, we have another workshop on geoidal model here in Uruguay. that that is a very focus on the practice of the program, of the graphs of program, following that methodology that we use. And we have this workshop has a theory first and test, and then the practice with the software. And it's already made. And I think it could be a good start for you, start to try all of the receipts and use the data you have, the gravity you have, the DTM that you can get from international sites or your own. I don't know if you have. And this is a question. Do you have any DTM, the local DTM or something like that, or not?
We are we don't have the separate DTM model, but we are using SRTM DTM model or different DTM model. So thank you for informing us about the workshop. We have another question from Maestapa sir. Please, you can ask the question directly, Maestapa.
Thank you, Dr. Walter, for this wonderful presentation. My question is mostly not about the processing part, but mostly I want to understand the geodetic infrastructures, like the control points and then labeling networks that you need to have before you process and get the geoid. So let's imagine a situation: you found a new country with no labeling network, no gravity network, no GNSS network, nothing. Then how would you start the process of getting the geoid? I mean, what would be the first, second, and like the third steps? What would you follow? Like if you have to restart from the beginning, what would be your steps to get this geoid?
Okay, thank you, Mahesh. I don't know if I spelled right, but okay. Start from the beginning. We don't have any geodetic information. You can use the global geopotential model in order to get undulations. So you can go to the International Center for Geopotential Models and ask for a grid of, you can choose a global geodetic model and ask for a grid of your data, of your area. And you can ask for a resolution and also for the model and also for the, if you want undulations or whatever you want. So if you have nothing, you can go to that international center and start with a geoidal model. That is very nice. So in the case that you have, let's go one step forward. You have a geopotential model, but you want to tailor this model to your country. So you have to have some GNSS stations with orthometric stations also, with the orthometric values also at the same point. So with that, you can tailor your geopotential model to your vertical data. That is when you have nothing but GNSS observations. That is another way to do it. So For geoidal model, you need three components: the geopotential model, the gravity data, and the terrain model. If you have some gravity data, you almost have everything, because global geopotential model, you can ask for a global model, and terrain model you can use, as was mentioned here, SRTM or better, or test another models, DPM models that are available and free now. So only you need this gravity data. If you don't have gravity data, it's very difficult. But I know that Nepal has at least more than 100 point of gravity data, and I don't know if it's available, this data are available or not to you. That is another question. There was a question here.
Okay, thank you.
There's a question here. If you have, the problem is LiDAR. LiDAR is very expensive. If you have that LiDAR survey on your country, of course it's better. But I don't know if you have. If you don't have, use SRTM or another one. I don't know if Mahesh, I don't know if your question was clarified or not.
Yes, Dr. Walter. Yeah, more or less. Further, I was looking into your country's gravity network, and I saw like 9 or 10 stations where you had measured the absolute gravity. I think in Nepal there's only one place where absolute gravity was measured, and it was maybe 20 years ago. So how important is it that we need some, at least few such absolute gravity stations? How important is it for Nepal to have it?
So I think some gravity stations are old ones. Sometimes the problem is to get the original survey, because when we readjust gravity network, you need the observations, and sometimes you just have the gravity value, but not the time, not the relative survey, and this is a problem. I think if you, I don't know if you have access to the gravity. Do you have a gravity database available in the country, or in some countries there are very restrict ones? I don't know. What is the Nepal situation? The gravity data is restricted or is free?
It is actually restricted, but since we work at the Geodetic Survey Division, we can have access. Some of our colleagues can have access to this data.
Okay, so if you have access to some gravity data, you have almost everything, at least to start with Geoid model, because you have the programs, you have the methodology, and you have your potential model. I have also global DTM, so that is almost everything. Let me show you here. I will try to find. There's a report. Okay. let me share again. So, are you seeing that? This is our technical report.
Yes, yes.
Our technical report for our geoidal model. You can find this report in the IGM site. The homepage, you can find this technical report. Here is explained everything, all the steps here that I made. And the nice part here is that after one here, I make a detailed presentation of everything that we need in the remove restore process and what is the GraphSoft software used for do that. And here also is the program and also the jar who is make this this magic. So this is, for example, TC program. In job 1B, I separate the René Fosberg jobs in several jobs, step by step. But here is mentioned everything. And here is how I treat all the blocks. And here are the calculation of the quasi-geoidal model with the program and the job to do it. And what are the results? So here are very well detailed all the program used and what about the result of the geoidal model. So this technical report, this is just statistic and the program from the GraphSoft package that use the magic to calculate the geoid. But inside the report, you will find all the details about how it was made here and the results. And also some equation here, something like, for example, the 0 degree term here, it was calculated, but I know present, of course, because it's too detailed. And here is detailed also which of the GraphSoft program was used to do that. So you have here a very well path to calculate a geoidal model. And almost if you have some access to the gravity data, you have almost everything to start to calculate your own gravity data. It's not necessary to be more accurate, but it's good to you install the program and playing with that. And you can then start to improve your geoidal model when we have better data. That is my advice to you, or I can say, in order to improve your or to start to play with your Nepal Geoid.
Okay. We have another question from Shankar Kesi, sir. Please, you can ask your question, Shankar sir.
Hello, Dr. Walter. Good morning.
Good morning, Shankar. Nice to hear you.
Yeah, nice to hear you, Dr. Walter. So my curiosity is about having two different models, that we have geoid model for orthometric height and another transformation model. So having these two models at the same time, will it create confusion to the users? Will it be that a problem or what?
Okay. Okay. Let me answer the question. That is why we make available the three models: the quasi-geoidal model, the geoidal model, and the transformation model. In our country, we are discussing right now which kind of altitude do we have in the future, if normal or orthometric. And I made this calculation because I would like to, personally, I would like to follow the orthometric height, because I think we have to be very close to the mean sea level and not a theoretical surface. And so we are in the process of discussing that in our country. This year, we are going to calculate the geopotential number for our new vertical datum, and then we have to decide which kind of altitude do we want for the future. So we make available all the three because we want to improve the discussion on that matter. And of course, this is a country decision. So we are trying to make our contribution to that. As I mentioned, my best wishes are for the orthometric, the classic all orthometric model about the mean sea level. But this is the reason, but this explained also in our homepage that we make available in the application also, we make available the three altitudes. And also the difference between, as I showed, the difference between the two surfaces are very, very small, it's some millimeters. So in the final, for our country, it doesn't matter which kind of altitude we are going to use. It's almost the same. But for a very high leveling network or very high leveling survey, as we are doing now in our capital, we need to transform from one surface to another. This is because we are working with the millimeter precision. So really, in Montevideo, we have 1 to 2 millimeters difference, and we have to account for that. I don't know if your answer was clarified, your question.
Yes, Dr. Walter. And my follow-up query is, so we need more number of GNSS and leveling station to derive transformation model, right, Doctor?
Yeah, in my country we need, and I think in every country is really a need to have more GNSS station over orthometric stations. This is for transformation the model to the geoidal model to the vertical datum. As I mentioned, you are destroying something like that, your geoidal model. But it's useful for application in cartography, topography, so that.
So if we have very few GNSS leveling station, then we have to stick to the Geoid model, or we will have a very less accurate transformation model.
Okay, your transformation model will be not so good. No, maybe it's not good to do it. And also you have to trust on in your GNSS and leveling in order to do that transformation. For example, that difference that we have in our last model, we think that this mainly because errors in the vertical network and not in the geoidal model. Because of that, we are working on the readjustment of our vertical network also. Besides the gravimetric readjustment, we are working on the vertical in order to improve also the transformation model.
Okay, Dr. Walter, thank you.
Okay. I have a queries regarding gravity reduction. You mentioned in your earlier slide, you used Fourier reduction, terrain correction, and Helmholtz condensation reduction for Urugeoid 110. So my query is about Nepal. Nepal has variable topographic condition, as we earlier talked. The topographic masses of Nepal is very huge. If we see from the minimum elevation for Nepal is 59 meter from sea level, and maximum is 88.86 meter. So what are the if only non-isostatic reduction are sufficient, or we need isostatic reduction for the gravity measurement? If you wish to answer, please. My question is about what are necessary gravity reduction technique for country like Nepal?
Okay, that is a good question. Terrain is always a challenge in Nepal because the very big mountain that you have, and any kind of reduction will have some will introduce some error on that because of the error of the data that is impossible to avoid. But I recommend to use as high anomalies, leave the station on the ground and not reduce to the geoid, because maybe you are making more mistake or introducing more errors reducing to the geoid that working with the high anomalies at the surface. I don't know if I was clear.
Okay, thank you.
Our first model in 2000 was I reduced the Fourier anomalies to the geoid through the normal reductions, everything, Bouguer, terrain correction, and finally our free anomalies were reduced to the geoid, and then I calculate a gravimetric geoid. But starting on 2007, we moved the methodology to work with the high anomaly and obtain the quasi-geoidal, but and then transform it to geoidal model. That could be also introduce some error because when you make this transformation from quasi-geoidal to geoidal model, you use the Bouguer anomaly. And the Bouguer anomaly also depends on terrain. So it's very difficult to answer. But I think the use of high anomaly is more clean in the process.
Okay, thank you. We still have time. If anyone have query regarding our topic, please you can ask directly, or you can leave your question in the chat box.
I will tell to the Nepalese engineer that put your hand at labor, put your hand at work. It's a question of start. And I will be here helping if you need. I know that in the name of my mentor and master, René Fosberg, that he will be also available in order to help. But as I told you, you can start working with the data you have and then try to improve it. Important is the experience that you are gaining. I don't know if Rene has some comments. Please.
Well, yeah, I think a great talk, Walter. I got most of it. I had to go briefly in the middle. I think it's a very good point you're making. I would just add that for the Nepalese survey, if you work with normal heights and cross-geoid, it's very easy in the end to convert to autometric heights and regular geoid. So that's something which is well established. So it is not a big issue whether you internally work with normal heights, and then for the average surveyor, you can work with the autometric heights. Of course, there's a difference in the way that the highest mountain, Mount Everest or Sagarmatha, will have be 4 meters lower in normal heights, and so you don't want to use that. You want to keep Mount Everest at the right level. And I appreciate very much the work you did with the Chinese and in making really the height official some years ago from the Department of Survey of Nepal. And I think, Walter, it's great. We can help with all these practical things. So great talks.
Okay, thanks, Rune. And you had a lot of experience, maybe from the air in Nepal.
Yeah, and I would say that Nepal is the biggest challenge for geoid anywhere in the world because of the very, very big changes over very small distances. So the 1 centimeter geoid you mentioned in Montevideo, and we have the same in Denmark. I think that would be a big challenge, possibly impossible to do in Nepal. But even at a few centimeter, you should be able to do that in the capital area, the Kathmandu Valley, Pokhara, and some of these big towns.
Thank you, brother.
Okay, thank you, Rene. Now, I think no one have any question left. So we are at the end of the episode. Dr. Walter, if you would like to add something in the end.
As I said, I am available to help you if you decide to start to work on a geoidal model. I will be available, of course, and if I cannot answer, maybe Rene can answer your doubts. And I think it's a question to start to work on that. And maybe if you need, I think that maybe your gravity network needs, as far as I know, you have only 1 point. Maybe 2 or 3 absolute gravity stations would be nice for your gravity network. And I know there will be some international institutes that can collaborate on that, or at least be contacted on that.
Okay. Thank you, Dr. Walter, for your wonderful presentation, for your time. I would like to thank, on behalf of Nepal Geomatics Engineering Society, I would like to also thank Rene Forsberg for joining us. I would also like to thank all of you for joining 9th episode of Geo series. We'll have another episode after 2 weeks. Till then, goodbye to all of you. Before ending this meeting, let's take a screenshot of this meeting. So if you are, if you can turn your video for last time, so we can take a photograph of this session. Then we will end this episode.
So thank you very much to you, and say Shankar and greetings. Thank Harun also. Bye-bye.
Bye-bye.
Bye-bye.